When you look at a massive industrial facility like a chemical plant or an oil refinery or even a giant power station from the outside, it just looks like this colossal, static mountain of steel and concrete.
Yeah, it really does. I mean, it just looks like giant plumbing, mostly.
Exactly. But if you were to somehow X-ray that facility, you wouldn't just see pipes, you would see this sprawling, incredibly complex nervous system.
Oh, absolutely.
Like millions of tiny sensors, wires, and pneumatic tubes all feeding back to a central brain, making thousands of micro decisions every single second. And today, we're looking at the exact instructions for how you build that nervous system. Welcome to the deep dive.
Thanks for having me. And, the blueprint we are unpacking today is formally known as a scope of work for instrumentation works. And it's governed by a framework called a FIDIC Red Book Construction Contract.
Right, and I know the phrase legal construction contract sounds, well, incredibly dry.
It does sound dry, yeah.
But this document is actually the boots-on-the-ground reality of how mega projects come to life.
Okay, so let's unpack this. Because, to put it simply, a FIDIC Red Book contract is this adversarial, highly structured set of rules.
Very adversarial. I mean, a contractor only gets paid for the physical work they can legally and mathematically prove they completed to perfection.
Which creates this fascinating dynamic where engineering physics basically crashes headfirst into legal paranoia.
That's a great way to put it.
And reading between the lines of all these, engineering codes and material specifications, you really start to see the story of how you give a massive, dumb steel structure the ability to see, feel, and react to its environment.
Right, because without it, the facility is essentially blind.
Yeah. So whether you are a project manager trying to orchestrate a multi-billion-dollar build, or an engineer in the mud, or just someone who is insanely curious about how the modern industrial world doesn't, constantly blow up, this is your playbook. And we're going to explore exactly how this facility physically feels its environment, how it breathes, the strict physics of its nerve pathways, and the highly choreographed human labor required to pull it all off.
Okay, so if we are building a nervous system, the first logical step is giving this giant steel body its sensory organs, right?
Exactly. It needs to know what is happening inside its own veins and stomachs, basically.
Right. And the contractor is tasked with installing this massive variety of devices to measure four main things, which are flow, temperature, pressure, and level. This is work breakdown structure, or WBS 900.
Right, WBS 900.
And I was looking at the sheer variety of these sensory devices just to figure out how fast a fluid is moving. You're installing vortex transmitters, Coriolis meters, ultrasonic sensors. But what really stood out to me was the intense engineering rigor required for something as simple as taking a temperature.
Yeah, taking the temperature inside an industrial pipe is clearly nothing like sticking a thermometer under your tongue.
I would hope not.
Far from it. I mean, you cannot just drop a delicate electronic temperature sensor directly into a pipe carrying, say, crude oil or high-pressure steam.
Because it would just melt or get crushed.
It would be destroyed instantly, yeah.
Yeah.
The flow would rip it apart. Instead, the contract specifies the use of a thermowell.
A thermowell.
Right. This is a thick, protective metal tube machined out of solid steel that is permanently welded or bolted right into the pipe. The actual delicate temperature probe then slides safely inside that protective well.
Okay, but the document doesn't just say, install a metal tube. It demands a massive mathematical proof for every single one. It says all thermowells must be wake frequency calculated.
Yes.
Why does taking a temperature require advanced calculus?
Well, we have to look at the fluid dynamics happening inside that pipe. Imagine you stick your arm out the window of a car on the highway.
Okay, sure.
The wind rushes around your arm and creates a turbulent wake behind it, making your arm shake.
Yeah, you can feel it vibrating.
The exact same thing happens to that metal thermowell inside the pipe. As high-velocity liquid or gas rushes past it, it creates alternating whirlpools, or vortices, on the downstream side. This phenomenon is called vortex shedding, and it causes the solid metal probe to vibrate rapidly.
So it's essentially fluttering in the current. But wait, it's solid steel. Why is a little vibration a problem?
Because every physical object in the universe has a natural resonant frequency.
Like a tuning fork.
Exactly like a tuning fork. If the frequency of those alternating fluid whirlpools happens to perfectly match the natural resonant frequency of the metal thermowell.
Oh, wow.
Yeah, the vibration amplifies exponentially. The metal will fatigue and very quickly just snap right off.
You're saying the fluid literally shakes the solid steel until it breaks.
It absolutely does.
And if that snaps, you don't just lose your temperature reading. I mean, have a jagged piece of metal flying like shrapnel downstream into delicate pumps or turbines.
Exactly. Plus, you now have a gaping hole in a high-pressure pipe spraying toxic fluid everywhere.
That is a nightmare scenario.
And that is the exact catastrophe the calculation prevents. The wake frequency calculation proves mathematically that the specific shape, length, thickness, and metallurgy of that one specific thermal well can survive the exact flow rate and density of the fluid in that specific pipe without vibrating itself to pieces.
And they have to do that for every single temperature point in the facility.
Every single one.
That perfectly illustrates the stakes here. But keeping with the sensors, I was reading the section on how they measure liquid levels inside the massive storage tanks, and suddenly the document mandates nuclear materials.
Yes. The nuclear level transmitter.
Wait, nuclear? Why are we bringing radioactive isotopes onto a standard industrial construction site just to measure how full a tank is?
I know, it sounds like science fiction, but a nuclear level transmitter is actually a highly reliable, standard solution for environments where traditional physics just fails us.
Fails us how?
Well, think about what a chemical plant might be processing. It could be highly corrosive hydrofluoric acid, or maybe a vat of molten sulfur at 1,000 degrees, or a really thick, sticky, abrasive slurry.
Okay, nasty stuff.
Extremely nasty. If you drop a mechanical float in there, it will dissolve or jam. If you try to bounce a radar pulse off the surface, the thick foam or steam will just scatter the signal completely.
So you basically bypass the inside of the tank entirely. You X-ray it from the outside.
In a manner of speaking, yeah. You mount a shielded box containing a radioactive isotope on one side of the giant vessel,
Okay.
and a highly sensitive radiation detector on the exact opposite side. The isotope constantly shoots a beam of radiation through the steel walls and across the inside of the tank.
And fluid blocks it.
Exactly. As the heavy, toxic fluid level rises inside, the fluid physically blocks more of that radiation from reaching the detector on the far side. The computer then calculates the fluid level based on the shadow. The sensors never even touch the acid or the molten sulfur.
Okay, mechanically, that is an elegant solution. But the scope of work immediately pivots to the logistical nightmare this creates.
Oh, it's a huge headache.
Right. You are no longer just an electrician running a wire. You are bringing a live radioactive source onto a bustling, chaotic job site full of welders, scaffolders, and heavy machinery.
And the health, safety, and environmental section, the HSE protocols, they treat this with extreme gravity. I mean, the contractor cannot simply order this part and bolt it on.
They can't just buy it off Amazon.
No, definitely not. They have to obtain specialized import permits, coordinate with national atomic energy authorities, and ensure that only personnel holding very specific radiation worker certifications handle the devices.
Wow.
They have to set up physical exclusion zones. A single line item for a sensor completely alters the safety profile and the project schedule for that entire area of the plant.
Okay, so we've built the senses. The facility has eyes and ears, and it can detect that the acid tank is overflowing. But that knowledge is utterly useless if the central brain can't physically turn a valve to stop the flow.
Which brings us to how the facility reacts.
Right, the muscular system, WBS 901 and 902.
Yeah. In heavy industry, electric motors are rarely used to turn the big critical valves.
Why not? Just too weak.
They're too slow, for one. But more importantly, electrical sparks are a massive explosion hazard in these environments. Instead, these facilities use pneumatics. They use highly pressurized instrument air to slam massive valves open or shut in milliseconds. If the sensors are the nerves, the instrument air system is the muscle.
And the scale of this system in the contract is just hard to fathom. The contractor is installing endless miles of 38-inch and 12-inch seamless 316 stainless steel tubing.
Miles and miles of it.
It branches off main headers like arteries down into tiny capillaries feeding every single valve. But what really caught my attention wasn't the metal, it was the intense requirement for the air going inside it.
The instrument air quality.
Yeah. The document mandates that this entire system must be blown clean and dried to a staggering dew point of minus 40 degrees Celsius before it can touch a single instrument. Why does the facility need to breathe perfectly dry alien desert air?
Well, let's follow the physics of ambient air. The air around us contains humidity, right? Gaseous water.
Right.
When the facility's massive compressors suck in that atmospheric air and compress it to, say, 100 or 150 psi to power the valves, they also compress all that moisture.
Okay.
If you send that pressurized humid air through miles of steel tubing that runs outdoors, and then the sun goes down and the ambient temperature drops.
Whoa, condensation.
Exactly. That moisture will rapidly condense. You suddenly have liquid water forming inside your pneumatic lines.
But, I mean, you're telling me a few drops of water inside a steel tube is a critical threat to a multi-billion-dollar refinery.
A catastrophic threat. That liquid water will travel through the tubes and enter the incredibly sensitive, microscopic internal channels of the digital valve positioners.
The brains of the valves.
Right, these are the precision pneumatic brains that control the big valves. Water causes rust. It carries microscopic dirt that clogs the tiny ports, and in colder climates, that water will freeze solid.
Which locks the entire mechanism in place.
Imagine an emergency shutdown system detects a runaway reaction, right? And it commands a critical isolation valve to slam shut to prevent a massive explosion.
Okay, high stakes.
But that valve is physically frozen open because a tiny puddle of condensation turned to ice inside the actuator. The plant is lost.
Wow.
That minus 40-degree dew point specification guarantees that no matter how cold the pipe gets, liquid water can never form. It is a life-saving metric.
It perfectly illustrates how an invisible microscopic point of failure can bring down a billion-dollar asset.
It really does.
And speaking of proving things won't fail, the testing requirements for this pneumatic muscle are intense. The contractor has to subject all of this instrument air pipe work to a leak test at 1.5 times its maximum operating pressure.
Yeah, this is a standard ASME B31.3 process piping code requirement, but it fundamentally changes the nature of the work. You are proving the system can handle extreme spikes in pressure.
Right.
But when you pressurize a piping system to 150% of its design limit using a compressible gas, like air or nitrogen, you are no longer doing plumbing. You are building a potential bomb.
Because unlike water, which, doesn't compress much, a gas stores all that mechanical energy like a tightly coiled spring.
Exactly. If a weld fails, or even if a single compression fitting wasn't tightened properly by a technician, all that stored energy releases instantly.
It just detonates.
It acts exactly like shrapnel. A failed half-inch stainless steel fitting under that much pneumatic pressure will fire across the site like a bullet.
Which is why the contract dictates strict risk assessments and method statements.
You have to clear the area, establish hard barricades, enforce exclusion zones. You cannot have painters or scaffolders casually walking past your manifold while you are testing it.
The coordination there is wild. You're not just installing tubes, you're actively managing deadly hazards in a shared workspace.
Exactly.
So we have the sensory organs and we have the powerful pneumatic muscles. But those two systems mean absolutely nothing without the physical nerve pathways connecting them to the actual process pipes.
And this the critical discipline of instrument hookups, WBS 903.
How exactly do we connect a delicate transmitter to a 24-inch pipe carrying hot, roaring gas?
We use impulse lines. They're very small, specialized tubing that taps into the main process line and routes a tiny sample of that pressure or fluid over to the sensor.
And I found a very specific, totally inflexible installation rule for these lines.
The gradient rule.
Yes. The document mandates that impulse lines must be installed with a minimum 1 to 10 slope, or gradient, angling back toward the process pipe.
It's crucial.
But if you are a contractor trying to build a clean, organized-looking facility, why can't you just run the tubes in perfectly straight horizontal lines with neat 90-degree corners?
Because, as we discussed with the air system, gravity and condensation do not care about aesthetics.
They really don't.
The contract explicitly states these lines must be free from pockets where liquid can accumulate. Let's visualize the physics here. You're measuring the pressure of a hot, humid gas flowing through a main pipe.
Okay.
As a tiny bit of that gas enters the small impulse tubing leading to your sensor, it cools down. The vapor condenses back into a liquid. If your tubing has a perfectly flat horizontal run, or worse, a slight dip, that liquid will pool right there.
It creates a tiny puddle, exactly like the U-bend trap under a kitchen sink.
Precisely. Now, think about what your pressure transmitter is actually feeling. It is supposed to read the exact pressure of the gas in the main pipe. But now it is reading the pressure of the gas, plus the heavy physical weight of that puddle of liquid sitting in the tube.
Ah, so the water is pushing against the sensor too.
Yes. This is called hydrostatic head pressure. Your sensor is now sending an artificially high pressure reading back to the control room.
Which means the central brain thinks the tank is overpressurizing when it's actually completely fine.
And the central brain reacts. It might trigger an emergency shutdown, tripping the entire multi-billion-dollar plant offline and costing millions in lost production.
Over a puddle in a tube.
Over a puddle. Or far worse, If the puddle creates an artificially low reading on a different setup, the brain might fail to open a relief valve during a genuine crisis.
Oh, that's terrifying.
By enforcing a strict 1 to 10 gradient, the engineers use gravity as an active safety tool. Any condensation that forms naturally flows backward down the slope and drains safely back into the main process pipe.
It is brilliant in its simplicity. But, as you step back from these tiny, perfectly angled tubes and look at the bigger picture of the contract, you hit the exclusions and interfaces sections.
The logistical puzzle.
Exactly. This is where the engineering stops and the project management nightmare begins, because the instrumentation contractor does all this incredible, delicate work, but they are surrounded by a massive list of things that are explicitly not my job.
It is the defining characteristic of modern mega projects. No single entity builds the whole thing anymore. The instrumentation contractor has a very tightly defined box, and they are highly dependent on the contractors working in the boxes next to them.
And the dependencies are just staggering. I mean, this contractor is installing all the sensors and running the signal cables, but they do not provide the distributed control system, the actual computer brain.
Right.
They don't pour the concrete foundations for their own equipment stands. And most surprisingly, they aren't even allowed to drill the holes or weld the connection nozzles onto the main pipes to install their own sensors.
Oh, the mechanical contractor has to do that.
If you have ever tried to manage a home kitchen remodel where the drywall guy is waiting on the plumber who is waiting on the electrician,
Oh, I've been there.
right? Imagine multiplying that logistical friction by 10,000. If the mechanical contractor falls behind schedule and fails to weld an instrument nozzle onto a massive vessel before a crane hoists it 150 feet into the air, the instrumentation contractor is entirely paralyzed.
They are just standing there on the ground with a highly calibrated $100,000 radar-level transmitter and nowhere to put it.
Or the electrical contractor is 2 weeks late installing the heavy steel cable trays, so the instrument crew has nowhere to safely route their fragile fiber optic signal cables. They can't just leave them coiled in the mud.
Exactly. And the contract actually mandates strict coordination with the piping contractor for a very dangerous reason.
What's that?
Well, when the pipers finish welding the main facility pipes, they have to hydrostatically pressure test them with water to massive pressures to prove their welds.
Okay.
If the instrumentation guys have already bolted their delicate low-pressure sensors to those pipes, and then the pipers pump the system up to 3,000 psi,
Boom.
all of those precision sensors will be instantly blown out and destroyed. Interface management is often vastly harder than the actual engineering.
Which perfectly transitions into the final massive piece of this puzzle. You cannot build this intricate, dangerous, interdependent system with a disorganized mob.
No, you need a highly synchronized human workforce.
And you need an ironclad mountain of proof that nobody cut corners. The scope of work heavily defines the labor categories. It doesn't just ask the contractor to provide workers.
Right. It legally defines strict grades of labor, from an L1 all the way down to an L7, and it dictates the exact scope of what each human is allowed to touch.
You have the L1 instrument supervisor acting as the orchestra conductor. You have L2 senior technicians handling the delicate computer calibrations. You have the L4 fitters, who are the craftsmen, actually bending those miles of stainless steel tubing to the perfect 1 to 10 gradient.
But the role that really dictates whether this whole project succeeds or fails under FAA Red Book contract is actually the L7.
The L7 document controller.
Yes. To understand why the L7 is so powerful, we have to revisit the nature of this contract. In a Red Book environment, performing the physical work is only half of the contractor's obligation.
What's the other half?
Mathematically and legally proving that the work matches the engineering ideal. If there is no paper trail, the physical pipe does not legally exist.
But why such an intense separation between the guy building it and the paperwork proving it? Why can't the L4 fitter just sign a piece of paper saying, yeah, I bent the tube correctly, it looks good?
Because on a multi-billion-dollar project with extreme safety stakes, you have to engineer out human laziness, fraud, and simple fatigue.
You can't just trust a guy at the end of a 14-hour shift.
Exactly. You need an adversarial verification system. The documentation requirements are this massive alphabet soup of accountability. The contractor must submit inspection and test plans, ITPs. They must submit factory acceptance tests, site acceptance tests.
And every single pressure transmitter must be calibrated using UK's accredited equipment.
Right.
UKS stands for the United Kingdom Accreditation Service. And this isn't just a casual stamp of approval. It means you can't just calibrate a safety-critical sensor using a $50 pressure gauge you bought at a local auto parts store.
Far from it. An accredited calibration device has the documented, unbroken chain of mathematical traceability.
What does that actually mean in practice?
It means the specific device used to test your sensor on-site was itself tested against a more accurate master device in a laboratory.
Okay.
And that lab device was tested against an even more accurate device, tracing all the way up the ladder to national and international physical constants for pressure and mass.
Wow.
You are proving, legally, that your reading of 100 psi is exactly what the universe agrees 100 psi is.
And the L7 document controller is the human funnel for all of this. The SOW states that every calibration certificate, every loop check signature, every marked up as-built drawing showing exactly where a tube was routed, and every pressure test record must be compiled, verified, and submitted within 30 days of completion.
Because without that mountain of accredited paperwork, the facility is paralyzed legally instead of physically.
The physical pipe is there, but the regulatory bodies will not issue the permits to introduce hazardous chemicals.
The insurance companies will refuse to underwrite the risk of a startup, and the employer or the company actually paying for the facility cannot legally accept the work.
Clause 16 of the contract on measurement and payment makes it brutally clear. You aren't paid for sweating in the sun and bending pipe. You are paid based on work executed and accepted by the lead engineer.
Which means, if the L4 fitter does a flawless job installing a complex pneumatic valve, but the L7 document controller loses the pressure test certificate and the calibration traceability,
The work is rejected.
the work is rejected. The contractor doesn't get paid a single cent for that valve until they can prove it on paper. The paperwork is the sole vehicle for financial survival.
It forces the contractor to maintain extreme discipline from the very first wake frequency calculation all the way to the final signature.
It really does.
Well, it has been a phenomenal journey through what initially looks like a completely impenetrable legal document. We started with the sheer scale of a mega project and x-rayed our way down to the granular physics.
Down to the bare metal.
Yeah. We saw how a facility gets its senses, using advanced fluid dynamics to keep thermal wells from shattering and radioactive isotopes to see through solid steel. We explored how it gets its powerful pneumatic muscles, breathing minus 40-degree desert air to prevent microscopic ice from causing catastrophic explosions.
And we saw how gravity is weaponized using a 1 to 10 gradient to keep the nervous system from sending false panic signals to the brain.
Right. And finally, we saw how this entire physical marvel is legally bound together by an army of specialized labor and a mountain of traceable, accredited paperwork.
It is a staggering achievement of human coordination. But I actually want to leave you with one final provocative thought pulled straight from the introduction of this scope.
Well, lay it on me.
The contract explicitly states that the contractor is responsible for everything written in the document, but also for any work that is reasonably implied or necessarily incidental to the completion of the works, even where not explicitly stated.
Wait, reasonably implied? That sounds like a terrifying legal trapdoor for a contractor.
It is perhaps the most dangerous and debated phrase in construction law. The contractor cannot claim extra time or money for things they should have known were necessary.
Wow.
But think about the mind-bending complexity we just explored today. If this intensely specific, multi-layered document governs just one isolated subsystem of a massive facility, imagine the chaos of the master schedule.
The thousands of moving parts.
Exactly. What happens when the instrumentation contractor's reasonably implied assumption about when an exclusion zone for a nuclear sensor will be clear violently clashes with the mechanical contractor's reasonably implied assumption about when they can pressure test a massive pipe to 3,000 psi in that exact same space?
That's a disaster waiting to happen.
The friction between those two assumptions is where mega projects are won or lost.
That thought alone makes you appreciate that these colossal facilities ever manage to get built and turned on at all. It requires thousands of minds, millions of perfectly machined parts, and an airtight legal framework to keep the nervous system from short-circuiting before it even takes its first breath.
It really is a modern miracle.
Thank you so much for joining us on this deep dive into the hidden granular architecture of industrial construction. And to you listening, the next time you drive past a massive glowing refinery against the night sky, remember, you aren't just looking at static steel. You are looking at a living, breathing machine built one wake frequency calculation at a time. Catch you next time.
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching, please subscribe, and see you next time.